This is a production of the Chemical Education Material Study.
Light has always fascinated, sometimes inspired humankind. Every bit of information we have about the solar system, the stars, and the cosmos is messaged to us by light. In the same way, light measurements reveal the structure of the atom. It begins with the spectrum of a hydrogen atom. Here is a filament in a tungsten lamp. As the filament is heated, it emits energy in the form of light. Although the light appears white to our eyes, when we pass the light through a prism, it is separated into a continuous spectrum of colors. The color of the light indicates the energies of the photons. We see that the tungsten lamp emits all colors. Hence, it emits photons of all energies. This is a gas discharge tube containing hydrogen. The light emitted by this tube is due to hydrogen atoms. Let's look at this spectrum. This time we see that only a few colors are emitted, as shown by these lines in the spectrum. Each line corresponds to just one possible energy change in a hydrogen atom. We see that very few energy changes occur. We learn these energies from accurate frequency measurements. Such measurements show us that blue photons have more energy than red photons. If we represent the energy of a red photon by an arrow, the higher energy blue photons need a longer arrow. The violet photons need an even longer arrow to express their energies. We can express these energies per mole of photons either in kilocalories per mole or kilojoules per mole. 43.6 kcal per mole for red photons, 58.8 kcals per mole for blue photons, and 65.9 kcals per mole for violet photons. These energy changes reveal the spacings between the possible energy contents or energy levels of the hydrogen atom. When all such spectral information is collected, we are led to the hydrogen atom energy level diagram. We begin with a simple picture of the hydrogen atom. At any given instant, the electron is separated from the proton by some distance r. The electron and the nucleus have opposite electric charges, so they attract each other. This attraction gives the atom a certain amount of potential energy. The amount depends on the distance r. The electron is in motion, and so the atom also has kinetic energy. The sum of these two kinds of energy is the total electronic energy of the atom. This sum expresses the laws of motion that apply to macroscopic particles. To fit the observed behavior of microscopic particles, like electrons and protons, the laws must be modified somewhat. As modified, these laws are called quantum mechanics. The mathematics of quantum mechanics are quite complex, but we don't need to consider the details of the calculations. Our interest is in the results that quantum mechanical laws give. This computer simplifies the task of carrying out the calculations. When the calculations are completed, the computer tells us the energy levels for a hydrogen atom according to the quantum mechanical description. Some of the differences between calculated values match perfectly the experimental energy changes observed in the hydrogen atom spectrum. Because of this agreement, we conclude that quantum mechanics provides an explanation for the specific energies observed for the hydrogen atom. Consequently, we believe the results quantum mechanics gives for those properties that are more difficult to measure. One such property is the location of the electron relative to the nucleus. Quantum mechanics does not tell us precisely where the electron is at any instant. It does, however, give us probability information about where it might be found. To see what this means, we will consider the lowest energy state in the hydrogen atom, which is called the 1s state. An analogy will help. This dartboard will help us understand the kind of probability information that we get from quantum mechanics. See where the dart hits. Observe the pattern of punctures. There are many holes concentrated near the bullseye. Toward the edge of the board, there are fewer punctures. These holes indicate the likelihood that the next throw of the dart will land in a given square centimeter. Where there are many holes, the probability is high. Where there are few holes, the probability is low. We see that, even though it is hard to hit the bullseye, the probability of the dart landing in a square centimeter near the bullseye is greater than the probability of landing in an equal area far from the bullseye. The computer has been programmed with the quantum mechanical equations to show where the electron might be found in the 1s state. As this pattern develops, we see that it resembles the pattern of dart holes, now centered around the nucleus. What does this plot tell us about the location of the electron? To answer this question, another analogy may be useful. The movements of a hummingbird around its nest. We use the hummingbird to represent the electron. The nest represents the nucleus. The nest is located in this small tree in a field of flowers. Let's represent this on a chart. Here is the nest in the tree. The hummingbird collects nectar from the flowers here and there around the nest. We'll keep a record on this map of the location of each flower the hummingbird visits. Here's one now. We mark the location of this flower on the map. Now it's over here. Plotting over a long period of time, a pattern develops. In this pattern, for a given area, the number of pins is much higher near the nest than farther away. Again, we have probability information. Thus, we conclude that the probability of the bird landing on a flower near the nest is greater than the probability of landing on a flower some distance away. We can discuss the average distance of the hummingbird from the nest, but sometimes the distance will be less than this average distance, sometimes greater. In any event, we see that there are no boundaries to the pattern. Occasionally, the hummingbird lands on a flower a great distance away. The plot of the hydrogen atom, which the computer drew earlier, has exactly the same meaning. Just as this map tells us the probability of finding the hummingbird a given distance from its nest, so this plot tells us the probability of finding the electron a given distance from the proton. As in our analogs, we see that the probability of finding the electron near the nucleus is much higher than finding it far away. Again, we find that there are no boundaries to this plot, for although the electron is most likely to be found near the nucleus, it occasionally may be found far away. A limitation of this plot is that it shows probability in only 2 dimensions. We can use animation to add depth to the plot. This probability distribution of electron location is called the 1s orbital of the hydrogen atom. We note that the orbital has no definite boundaries. It is spherical in shape. The term 1s implies the lowest energy state, 1, and the spherical shape of the orbital, s. But remember that the orbital represents only the probability of finding the electron at a certain location at a given moment. If we could observe the electron at any one instant, the electron would be found at some particular location. At another instant, it would be found at some other location. What about the path or trajectory that the electron follows in getting from one location to another? Well, this is a question that quantum mechanics does not answer explicitly. Any trajectory that corresponds to the spatial distribution we see here could be in accord with quantum mechanics. For example, here is a possible model of the electron's trajectory. It shows the electron moving around the nucleus in a path similar to a planet moving around the sun. If this satellite model were correct, the electron would always be at a fixed distance from the nucleus. Then the probability plot would take the form of a circle. The electron would never come very close to the nucleus. Since the satellite model never places the electron near the nucleus, it is inconsistent with our experimental knowledge of atoms and can be discarded. Although quantum mechanics does not tell us the detailed motion of the electron in the atom, it does tell us the electron position in terms of probability. We can consider an average radius of the electron position, but there are no boundaries to the atom. The probability becomes 0 only at an infinite distance from the nucleus. Hence, the 1s orbital has a surface at infinity where the probability of finding the electron is 0. Any surface where the probability is 0 is called a nodal surface. The 1s orbital with this one nodal surface can be further characterized by the energy needed to pull the electron away from the proton. This is found to be 313.6 kilocalories per mole of hydrogen atoms. Since we have to raise the energy of the electron to get it away, we will designate the energy of this state to be minus 313.6 kcal per mole. We have already seen that the quantum mechanical model of the atom involves higher energy states, and that these are consistent with the hydrogen atom spectrum. Numerical analysis of the energy values shows us that these experimental energies are very simply related. For example, the 78.4 kilocalories energy value can be rewritten this way. 78.4 is just 1/4 of 313.6. 34.8 is just 1/9 of 313.6. These numbers are most conveniently recognized as 313.6 divided by the square of an integer. Thus, 4 is 2 squared, 9 is 3 squared. The lowest energy is 313.6 divided by 1 squared. We can characterize each energy level by this integer in the denominator. The integers are possible values of the principal quantum number, n, and we can use the integers to label the energy level. Now let's use the quantum mechanics to plot the orbital of the second energy level, the 2s orbital. Each point has the same significance as a point on our map showing where the hummingbird was seen. The pattern of points describes the 2s orbital in probability terms. Let's compare this 2s orbital to the 1s orbital. They are shown here, plotted to the same scale. Note that in the higher energy 2s state, the probability of finding the electron at a larger distance from the nucleus has increased considerably. Though this plot doesn't show it, the 2s orbital, like the 1s orbital, is spherically symmetric in 3 dimensions. Both the 1s orbital and 2s orbital show that the electron is sometimes found a very large distance from the nucleus, again reminding us that the atom has no boundaries. For the 2s orbital, however, we see a new characteristic. There is a definite radius at which the electron is never found. Since the orbital has 3-dimensional symmetry, this radius defines a second spherical surface at which the probability of finding the electron is 0. Such a surface, you'll recall, is called a nodal surface. Thus, whereas the 1s orbital had only one nodal surface at infinity, the 2s orbital has 2 nodal surfaces, one at infinity and one at a specific radius. Quantum mechanics shows that there are other orbitals for hydrogen with the same energy as the 2s orbitals. Here, the computer is plotting one of these. This is a 2p orbital. This 2p orbital has about the same average size as the 2s orbital, but note the striking difference in the contours of the 2 orbitals. The 2s orbital is spherically symmetric, but this 2p orbital is definitely oriented along one axis, in this case, the z-axis. Let's use animation to show the other 2 axes, the x and y axes. This 2p orbital, like the 2s orbital, has 2 nodal surfaces at which the probability of finding the electron is 0. One nodal surface is at infinity, but the second for this 2p orbital is in the xy plane. But why isn't the orbital oriented along the y-axis or the x-axis? The answer is that there are 3 independent orbitals of this shape, one oriented along each axis. Each of these 2p orbitals has 2 nodal surfaces, one at infinity, the other a plane through the nucleus. We can now picture our energy level diagram like this. We see that there is only one orbital for the lowest energy level. This 1s orbital, you recall, has only one nodal surface. But for the energy level corresponding to n equals 2, there are 4 orbitals, each having 2 nodal surfaces. In fact, for every value of n, there are n squared orbitals, each having n nodal surfaces. We see then that the quantum number n, called the principal quantum number, gives a great deal of information about the hydrogen atom. It indicates the possible energy states and their corresponding energy values of the hydrogen atom. For each energy state, there are n squared orbitals, and each orbital has n nodal surfaces. When we plot still higher energy orbitals, we see that they become more complicated in shape as n increases. But in quantum mechanics, all orbitals are described in probability terms, just as we described the 1s orbital. Our starting point was the experimental energy levels of the hydrogen atom. Because quantum mechanics is a way to calculate these energies exactly, we investigated it further. The quantum mechanical description of the atom contains only probability information, like the pattern of punctures in the dartboard, and like the map of the flowers visited by the hummingbird. Chemists have found that quantum mechanics also explains many other concepts of chemistry, such as the energy levels of many electron atoms, the formation of molecules, bond energies, and bond lengths. It explains why the elements form the periodic table. It also tells us why hydrogen burns, why proteins and DNA have helical structures. Thus, the quantum mechanical view of the atom provides a basis for understanding all of chemistry.